Good day, I'm Smriti Mahajan. In this lecture, we will learn about the statistical properties and scaling relations of galaxies. Scaling relations are general relations between any two observable properties of galaxies, as you will see shortly. Let's start with the property you are already aware of. This is a distribution of the G-R optical color of a set of thousands of nearby galaxies. Distribution of any optical color for a set of galaxies would qualitatively look like this, that is, bimodal, because some galaxies are red and others are blue. But this distribution will vary for different samples. For instance, here you see from top to bottom the color distribution for another sample of galaxies subdivided by their magnitude as mentioned in the top right hand corner of each plot. It is noticeable that low luminosity, that is low mass galaxies are mostly blue. As the mass, that is luminosity increases, galaxies are more likely to be red, hence the change in the relative peaks. This trend in color with luminosity is widely used to separate the galaxies into the blue cloud or the red sequence as we saw in an earlier lecture. This bimodal distribution is likely a result of different dominant stellar populations in the red and blue galaxies. This figure shows that the color versus stellar mass bimodality exists in all environments. The panels from A to F represent bins of increasing environmental density as mentioned in the bottom right corner of each plot. And you can notice that the contours representing the number density of galaxies in this two-dimensional color stellar mass space keeps changing, but exists in all panels from very low dense environments to the highest density environments, which are likely found in the centers of massive clusters and groups. Another important relation exists between the stellar mass and metallicity of galaxies, as shown on this plot. The simplest interpretation for the mass dependence of metallicity is that galaxies lose metals via galactic winds, for example, supernovae outbursts. Galaxies with shallow potential well will lose more mass, that is, they have more efficient outflows, more efficient ways of throwing away metals. The scatter observed in the mass metallicity relation is correlated with other physical properties as well. These correlations provide clues to the origin of the mass metallicity relation. It is also noteworthy that the mass metallicity relation evolves as a function of redshift. We believe this is because the high redshift galaxies were metal poor relative to the redshift 0 galaxies, which have had enough time to accumulate metals from various sources such as supernovae explosion. In this plot, you see the mass metallicity relation at redshifts greater than 2 and for the present day galaxies. The luminosity function. Just like we learned about the stellar mass function, which gives us estimate of the number of stars of each magnitude forming in a cloud, one can use the luminosity function to estimate how common are galaxies of any given luminosity. A luminosity function gives the number density of galaxies as a function of luminosity. It can either be expressed in luminosity or absolute magnitude. Phi of L is the number of galaxies per unit volume with luminosity between L and L plus dl. Phi of M is the number of galaxies per unit volume with absolute magnitude between M and M plus dm. Integrating over the luminosity function will hence give us the number density of galaxies in a given volume of the universe. The functions can often be expressed as phi of L dl equals phi star by L star into L by L star to the power alpha e to the power minus L by L star dl, and correspondingly in terms of absolute magnitude. Measuring the luminosity function requires a knowledge of the distance to the galaxy in order to measure the luminosity, and the knowledge of the selection function, that is, what kind of selection biases exist in the sample. For instance, I can have a sample of cluster galaxies only, I can have a sample of red galaxies only, I can have a sample of spiral galaxies only, etc. Luminosity functions are usually well characterized by a Schechter function. The three parameters of the Schechter function, which is parameterized here in this figure, are L star, which is the luminosity of galaxies near the break, which is often referred to as the knee in the luminosity function. Phi star is the density of galaxies of luminosity L star, as you see marked in this plot. Alpha is called the slope of the luminosity function at the faint end. Now, astronomers like the Schechter function because it is relatively simple, does a decent job of fitting the observations, and it is easy to deal with analytically. However, there are dangers of using it. First of all, note that the density of galaxies appear to grow without bound as one looks at fainter and fainter luminosities. If we were to extrapolate to very low luminosities, the Schechter function predicts an infinite number of galaxies or an infinite amount of light, neither of which is correct, obviously. One must also keep in mind that these fits are based on observations which had various sorts of biases, some of which I already mentioned. Very luminous galaxies, for example, are rare. We don't see any galaxies with J-band absolute magnitude greater than -24 near the local group. So we must rely on samples covering huge volumes and large distances to count the galaxies. But at very large distances, we then cannot detect the very common kind of galaxies, which are the low luminosity galaxies, which are found in abundance in the local group. Hence, in order to make a plot like the one shown here, we must mix and match results from different surveys, each of which have their own sets of biases. In a nutshell, this is a very complicated business. Here is another representation of the Schechter function fit to observed data points, but now we have split the data by limiting magnitudes. Notice how the limiting magnitude changes the fit at the faint end. The fit to the luminosity function will also change if we split the sample, say, by the morphology of galaxies, as done here using the three different colors. Furthermore, luminosity function of each morphological type also evolves with redshift, just like here, as shown at the bottom right of each panel. And that further adds to the complications. The luminosity radius relation. Ellipticals or early type galaxies show a tight relation between their luminosity and size. The left and right panels here show two samples in low and high density environments respectively. The luminosity radius relation for early type galaxies is statistically indistinguishable in different environments, although the scatter in the reddest galaxies is found to be lower relative to their bluer counterparts. Another way of saying the same thing is using the dn sigma relation, where dn is the physical scale of the galaxy defined at a specific surface brightness level. dn is equivalent to small dn into r, where small dn is a measure of the angular size of the galaxy and r is the distance to the galaxy. In this figure, you see this relation for the ellipticals on the left and S0s on the right. The fundamental plane. Fundamental plane is a relationship between luminosity, size, and velocity dispersion for elliptical galaxies. The term fundamental plane was coined by Jergowski and Davis in 1987. Fundamental plane can be expressed in many different notations using different combinations of the three quantities involved. This connection between dynamics, luminosity, and size is seen in all optical wavebands. The reason for constituting such a relation lies in the fact that the scatter and the scaling relation reduces greatly when a combination of two rather than individual parameters are plotted against one another, as you see in this example here. In panel A from Diaz and Muriel, a more recent version of this relationship is shown. It is obvious that when we plot the luminosity of galaxies as a function of velocity dispersion, there is a lot of scatter around the observed trend. The relationship looks remarkably tighter in plot B, where we now plot luminosity as a function of size. However, in panel C, we find a highly scattered relation between the size and the velocity dispersion. Although there is a trend that bigger galaxies have higher velocity dispersion. Hence, maybe the connection between radius and velocity dispersion does run exactly along the same lines as the connection between radius and luminosity. In that case, we could improve the quality of the relationship by throwing all three quantities into a bigger blender. If we mix them up in just the right proportions, we can find a model which matches the observations better than the simple linear ones. For example, as you see in the panel D in this figure. The Faber-Jackson relation for elliptical galaxies is a two-dimensional projection of the fundamental plane on the luminosity-velocity plane. It is equivalent to the Tully-Fisher relation for spiral galaxies. It is an important scaling relation found among elliptical galaxies only. Since the rotational velocity of ellipticals cannot be measured, of course, due to their morphology, we use the central velocity dispersion of stars, hence giving us a relation of the form luminosity proportional to some power of the velocity dispersion of the central stars. Often, this power has a typical value of 4, but it can vary in the range between 3.4 and 5.6. Sandra Faber and Robert Jackson showed in 1976 that the galaxies with large velocity dispersions tend to be more luminous. But it is well known that galaxies with high velocity dispersion also have high mass to light ratio, as you see in the bottom plot here. Since velocity dispersion is correlated with absolute magnitude, this means that mass to light ratio is also correlated with absolute magnitude. But how do you measure the velocity dispersion of stars in external galaxies? Now, most elliptical galaxies do not have a significant rotation. That is, the motion of the stars within them show little evidence for a common direction. However, in some galaxies, the stars move very quickly in their orbits. These tend to be the massive ones, and in others, the stars move relatively slowly. One way to quantify the motion of stars in such systems is by the dispersion of their velocities. Mathematically speaking, if we could measure the radial velocities vi of n individual stars in a galaxy, which we of course cannot in almost all cases because we cannot resolve individual stars in external galaxies, the velocity dispersion sigma would be calculated using the standard formula. In most galaxies, we cannot distinguish individual stars. So when we take a spectrum, the light of many, many stars is all mixed up, yielding a composite spectrum of the entire population. Since some of the stars are moving towards us and others are moving away from us, while some have no radial velocity at all relative to us, features in the composite spectrum, smearing out the spectrum in the wavelength space. The larger is the range of the motion, the larger is the degree of smearing. Let's see an example. Consider this single K33 star at rest with respect to Earth. The spectrum is taken from a single stellar population model library called Stellib. If an identical star now moves away from us at a speed of 100 kilometers per second, its spectrum will be shifted to longer wavelengths. If the light from those two stars is mixed together, the result is a spectrum in which the features are slightly diluted. But now if a system contains stars with a wide range of velocities, then the integrated spectrum will look smeared out compared to the original. Faber and Jackson measured the velocity dispersion in their sample of elliptical galaxies by comparing the spectrum of light from the center of each galaxy to a series of synthetic spectra in which a single template spectrum was broadened in a series of steps. When they compared the velocity dispersion of each galaxy to the absolute magnitude of the galaxy, they found a pretty good correlation. Galaxies with larger velocity dispersions tend to be more luminous. But what do these relations mean physically? The virial theorem tells us that the kinetic and potential energies of the bodies must be related such that twice the kinetic energy is equivalent to negative of the potential energy. Consider a simple model of a spiral galaxy. A big mass, capital M, is at the center, which is the bulge and the core of the spiral galaxy, around which a small clump of gas with mass small m moves in a circular orbit of radius r. Now in this model, the gravitational potential energy and kinetic energy of this spiral galaxy will be given by minus gmm by r and half mv square respectively. Solving for the velocity, we now get the velocity as square root of gm by r. But now suppose that if the mass to light ratio of all spiral galaxies were constant, then the velocity squared will be proportional to the luminosity, which is the Tully-Fisher relation for spirals that we derived in the last lecture. Even when the distribution of mass is more complicated than the Keplerian case, the velocity dispersion of stars will have a similar connection to the total mass and radius of the system. Sigma squared equals some constant into mass to radius ratio. Now let's again assume that the mass to light ratio is roughly the same for all systems, so that we can again replace mass with luminosity. Hence, sigma squared is proportional to luminosity to radius relation. At this point, we must make another assumption. Suppose that the surface brightness of galaxies is also a constant. Now, this is obviously not true in reality, but for ordinary large ellipticals, it is not an incorrect statement. If we make this assumption, then we can get a mathematical connection between luminosity and radius, that is, radius is proportional to square root of L. Now, if you put the previous two equations together and solve for luminosity in terms of the velocity dispersion, what do you find? You will find that luminosity is proportional to sigma to the power 4. Of course, we oversimplified in the derivation above. All elliptical galaxies do not have the same average surface brightness or central surface brightness. The giant luminous galaxies have somewhat lower central surface brightness than their smaller counterparts. But among the giant ellipticals, it is not wrong to say that they all have comparable average and central surface brightness. But it is due to additional complicating relationships between surface brightness and size that we can reduce the scatter in our model by moving from a fundamental line in a log-log plot to a fundamental plane. I end this lecture here. Thank you.